All right, chapter 7, gases, liquids, and solids. You're probably saying to yourself, didn't we already cover these earlier? We know what a gas, a liquid, and solid is. Yeah, but there's more to it than that. It's like I've got 13 sections to get through. We're going to look at the heart of this material is the gas laws. And then the kinetic molecular theory actually ought to come afterwards, but it is what it is. So what is the kinetic molecular theory of matter? Well, first of all, here's a reminder. This is just a review. Physical properties of matter, right? We can identify what we can see and touch and taste and smell with our senses. And these are some of the things that we can derive from it, both qualitatively and quantitatively. Like volume is a quantitative measure, right? So we can measure the volume of anything. We can measure its shape, right? If it's a regular shape, that's a lot easier. Okay, those two. And then we can calculate, we can actually measure volume and mass and use those two to calculate density. I remember that one. And these two are extensive properties. In other words, their values change with the amount of material. We have more material and more volume, and more mass. But when we ratio them to give you the density, that's an intensive property. In other words, it doesn't matter how much you have, that property is the same. It's constant. Compressibility is something that we see in gases, but not so much in liquids or solids. Definitely not solids. Compressibility actually has been demonstrated in some liquids. In fact, water. I'll talk about that in just a minute. Compressibility. Thermal expansion. We know that if you heat something up, it's going to expand, especially liquids and definitely gases. I remember when I was a kid, I lived in a suburb of Atlanta, and we weren't too far away from railroad tracks that ran through. There's a place called East Point. And I think it was East Point because it was an eastern point on the rail lines at one time. And I saw some machines out on the next to the tracks laying new track. And they had car after car after car after car and a single rail running all the way down those cars. And up to that time, I knew that rail segments were like, I don't know, 10, 12 feet long. And then they had a gap in them. And I learned pretty quick, even as a youngster, that gap in there was for expansion. Right? So when they heat up in the summer, which they do in Georgia, they'll expand. And they have, what do they call them, brackets, holding the ties together with expansion capability also. But then they came along with these mile-long rails, and they were laying those down. So I looked into it, and sure enough, it had to do with the thermal expansion. They had created a steel that had very low thermal expansion. So you could put in extremely long segments before you had to put a joint in. And that made for smoother rides too, because right, if you ride a train on old tracks, you'll hear it click, 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 click. And depending on how fast you're going, it might be click, 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 click. You're doing 70, 80. I've done 85 miles an hour in a passenger train. That was kind of scary, actually. Okay. So compressibility just means that the measure of the volume changes with pressure, external pressure on the substance. So we know if you compress a gas, if you increase the pressure, it's going to shrink. Well, they've also discovered actually measured. And if the gas or if the substance is compressed, that means the volume decreases. So if the denominator decreases and the numerator doesn't, then density has to increase. So they measured density of water in the oceans at a mile, mile and a half deep. And they found that the water at that depth was denser. It was actually experiencing compression. But for our purposes and the pressures that we're going to impose on liquids, they're not compressible. And then some fluids are specifically designed not to be compressible, like hydraulic fluid in equipment. You don't want it to compress. You want to deliver that pressure from one end to the other, from the supply end to the what do you call it, the use end. You want it to be that same pressure when it enters the hydraulic piston and operates the machine. And I've heard the story about the SR-71 Blackbird airplane, that its hydraulics were under such high pressure, the ground crew had to be really careful, because if it was pressurized and that thing sprung a leak and you were in the way, it would cut you in half.
One of my buddies in high school, his older brother was in the Navy, and he worked, I think it was aircraft carriers.
Okay.
In like the engineering department.
Uh-huh.
And some of their cooling lines, I guess,
Okay.
were under such high pressure that if they would walk through certain areas, they would take a like broomstick and have a string with a nut tied to the bottom of it and walk along with that. So if you were walking and there was any kind of leak that you couldn't see, cut the string and drop the nut so you didn't walk into it.
Oh,
yeah,
that's pretty smart.
Well, I didn't believe it the first time I heard it, and then I started looking at some of it, and I was like, yeah, you know, you got a 2-foot line and it's under a couple 100 pounds per square inch. That's a lot of pressure.
Yeah, and they can spring those pinhole leaks and you won't see it. The material might be invisible too, especially if it's one of those gases. It's a liquid under pressure, but as soon as you let off the pressure, it turns to a gas, but it's still moving pretty fast. If it was a cooling line, that's probably.
That might be it. I
Yeah.
have no idea. Couldn't recall that, but scary.
I used to work with a jet mechanic for the Air Force, and his hearing wasn't too good, even if you wear protection. Okay, thermal expansion. I mentioned thermal expansion before. If you increase the temperature, you've got different types of thermal expansion. There's linear, which is the one I described earlier with the rail lines. When they heat up, they expand. Actually, they in 3 dimensions, but the one we're concerned with their use is linear. There's also area expansion and volume expansion. And depending on the material that you're dealing with, its original state and the engineering that's involved, you may be interested in one of these versus the other. Now, gases, they're usually interested in volume expansion. So if you heat it up and the volume expands, then the density is going to go down. All right. Let's see. This just summarizes some of the things I told you and came straight out of your textbook. I just put it in there to be sure I covered all my bases. Okay. Oh, the most interesting fact, if you have say you've got a washer. Let's make a big washer like this with a hole in the middle. And if you heat it up, is that hole going to get smaller or bigger? you would think, I mean, if you've never been faced with this question before, you would think that the hole would get smaller because it's expanding in all directions. It gets bigger, yeah.
I was that confused for a minute, like. I know if you've got a bolt or something that seized up. You heat it up and it'll come loose. But. I never thought about it until now.
There are probably several effects that are occurring there. When you heat it up, you're increasing the kinetic energy of the particles between the threads. That helps loosen them up. But you're also expanding the size of the hole. And if you heat it from the outside, then it's going to heat up before the bolt does. But you heat up the out of the threads that the bolt goes into,
Yeah.
then it'll expand faster than the bolt will. And that should free it up also. Yeah. Okay. Kinetic molecular theory. I usually in my New River courses, I usually do this one after we've covered the laws, because historically speaking, the laws were usually discovered and described first, and then the theory comes afterwards to explain the laws. But the way these authors present it, they give you the theory first. And so here it is. You have certain propositions for the kinetic molecular theory. Remember, theories try to explain why something happens. So, actually, you can look at the title and derive some information from the title, right? We're talking about molecules, right? Very small things, which is not unusual from the beginning chemistry. But the kinetic part tells you a lot. These particles are moving, and they're not just moving themselves, vibrating or moving in a straight line. They're also smacking into each other. And that's the important part. So first premise is small, and they leave this one out, small, numerous, lots of particles. Now that's because it's, when we study something, we're studying enough of it that we can weigh. So there are going to be lots and lots of atoms and molecules in there. But there's another reason that we need to consider lots of particles. And that's because we deal with these trajectories of the particles and how they interact with one another on a statistical basis. And the larger the sample size, the lower the statistical error. So we consider large numbers of particles. We don't have the computing power, even with the fastest supercomputers, to track every particle, its trajectory, and its impact on other particles. There's not enough computing power. Now, maybe we'll eventually be able to do it if they ever get the quantum computer put together, right? Because it's supposed to be 3, 4, 5 orders of magnitude more powerful than the most powerful supercomputer we've got. Okay, back to this premise. Small, numerous particles. They have definite size, and they do not change. Small size. That's the first premise. Second premise is the particles are in constant motion. Now, sometimes that motion is vibration, but very often the motion is linear, especially for gases, right? In fact, the kinetic molecular theory was first proposed for gases. And then it was expanded to incorporate liquids and solids. And to determine the kinetic energy of something, that means with constant motion, that means it has a velocity, like not volume, but velocity. And that means if it has mass and it has velocity, we can calculate the kinetic energy of each particle with this equation. You need to know the mass, you need to know its velocity, and you can calculate the kinetic energy of the particle. Now, the only time that the kinetic molecular theory, this premise, would drop to zero is at absolute zero. There's no kinetic energy at all at absolute zero. So I think it's fairly safe to say that some of the particles, most of the particles, statistically significant number of particles in a substance will have kinetic energy, because we're not going to reach absolute zero. All right. These particles interact with one another. Now, if it's a solid, their motion is going to be vibratory. So they'll have kinetic energy in this direction, and then it'll go back to this direction and that direction. It's a periodic motion, it goes back and forth. But for liquids and gases, especially gases, you're going to have linear motion, and these particles are going to smack into each other. They're going to interact. Now, the ideal condition for kinetic molecular theory is that there is no interaction between the particles. When they hit each other, they act like billiard balls. They just impact and bounce off. Conservation of momentum. But in reality, I mean, once we get the ideal well grounded in our minds, then we can introduce reality. And the reality is that particles do interact with one another. They have electrostatic interactions are the majority of the interactions, an attraction or a repulsion. If you have ions, then if two positive ions approach each other or two negative ions approach, they're going to come in at huge velocities, and then they're going to resist that impact. That's one of the reasons that nuclear power, nuclear fusion is so hard to obtain, because the nuclei are positively charged, and when they get close together, they're going to resist. So you got to get them going fast enough. That means lots of heat, and you have to have very dense plasma, which would increase the number of impacts. And if you get the energy high enough, then you can get those nuclei close enough. Now the electrostatic interaction is overcome by the strong nuclear force, and that's when they fuse. But we're talking chemistry here and not physics, except for this right here. That's definitely physics. But they interact with one another, and if they're positive or negative, and even if they're not fully charged, they're not ions, but they're polar. In other words, one side of the molecule is just slightly negative and the other side is slightly positive. Then you'll have some interactions. Now, potential energy, let me see. Let me look at my hard copy. Maybe I better say a word. Say a word about potential energy. There are different types of potential energy. Did we talk about this before, or am I thinking of another class? Did we describe potential energy before? I don't
think so.
know.
Yeah, that's not the-
Yeah. So potential energy versus kinetic energy. If the object is moving, it has kinetic energy. but it can also have potential energy. And potential energy manifests itself in different ways. It can be as a result of position. Any object can have potential energy based upon its elevation, its distance from the center of a large mass. I'm talking about gravity fields here. So if I go up on the roof of this building, I have to climb stairs and I have to probably climb a ladder, get up on the roof. I have added to myself potential energy based upon my position in the Earth's gravitational field. I'm higher, further away from the center of the Earth. That means I have to add energy to myself to get to that position. Well, I can get all that energy back, right? Really simple. Just jump off the building. And when I hit the ground, I've got all my energy back as kinetic energy. All that potential energy is now kinetic. And right before I break a leg or smash my head or multiple internal organ ruptures. That's potential energy of position. But for our purposes, well, there's one other one that I want to get to before I get to the chemistry one. Condition. We're usually referring to potential energy of condition, which could be temperature, right? If you increase the temperature, you're increasing the potential energy of the substance. You're also increasing its kinetic energy. Temperature, pressure. Put a gas under pressure, you stored energy in it, and you know you've got stored energy, say in a 2000 or 2500 psi gas tank. All you have to do is lay it on its side and knock the top off of it, and you got a rocket, and you get your energy back. You stored energy in the condition of the gas under pressure. And the one we're most interested in is potential energy of composition. For chemists, composition is chemical bonds. Some chemical bonds are more stable than others, and those that are unstable have stored energy, right? A perfect example of that is nitroglycerin. When you create nitroglycerin, you're storing energy in the chemical bonds of that molecule, and all you need is just to initiate its decomposition. Pure nitroglycerin, I mean, if you just look at it cross-eyed, it'll decompose. But if you're Alfred Nobel and you figure out that if you mix it with kieselguhr, which is a type of clay, in a certain proportion, you can make dynamite and it's more stable. And then you would need an initiator of some kind to get it to go off. Of course, if you find a box of dynamite and you open it up and you see that those sticks in there are sweating, that's not water. That's liquid nitroglycerin. It's sweated out of it. Back off slowly and call for a hazmat team, explosives experts. And hope that you found the box in an explosion-proof cabinet or a building or one of those earth mounds that they build to separate munitions. One of my favorite movies is The War Wagon with John Wayne. And they were going to blow up a bridge. And they used pure nitroglycerin in little pint whiskey bottles. And that, I mean, that was fairly realistic the way they portrayed it, because in that southwestern US heat, and just a little bit of jiggle and those things would have gone off. Everything went okay though. Okay. So those are types of potential energy. Excuse me. Now you can get condition can also be charge. Right, if you have charged particles, think of it like two magnets. If you have two magnets with a north and a south, and you bring them together with their north poles facing each other, right? You're going to have to push them together. Say you want to put them to where they're touching. You've got to put energy into it and hold them there. If you want that potential energy back, all you have to do is let go and they'll go. Or if you have a north and a pole and a south pole, they want to be together. So what you do, you have to put energy in to separate them. And then if they're not too far apart, then you turn them loose and they snap back. That's one lesson I learned the hard way with these rare earth magnets that you can get out of hard drives. When a hard drive fails, I usually break it open and pull the magnet out of it and use it on my refrigerator. But those things are have a very strong magnetic field over short distances. So if you get your finger right too close to one, it'll snap down and pinch and leave a blister on your finger. Okay, enough of that. So we mentioned kinetic energy here. We're measuring kinetic energy of individual masses. But if we're talking about a large collection of atoms or molecules or ions, like I said before, our computing power can't track every particle. So what we do is we go for average kinetic energy. And a measure of average kinetic energy, is proportional to temperature. Right, so temperature is our measure of average kinetic energy of the particles in a system. All right. Let's see. All right, I left that one out. This is actually corollary. 4 is corollary to 2. This is average kinetic energy. And then 5 is how these particles interact with one another. They transfer energy when they impact one another. And the collisions are assumed to be elastic collisions. If you've had, have either one of y'all, or actually Zoomers, had any physics at all, physical science class or pure physics? Okay, so you know the difference between conservation of momentum and conservation of energy. Right? They are both conserved in a collision. But conservation of momentum, momentum is mass times velocity. Right? So if you have if you calculate the momentum of your particles, then the combined momentum of the particles after the collision is going to be the same as before the collision. Whereas kinetic energy is only conserved in 100% elastic collisions. Right? So if the collision is completely elastic, all the kinetic energy is conserved in the collision, and the kinetic energy of the particles that impact, when you add them together, it's the same before and after the collision. If it's an inelastic collision, then you lose kinetic energy. Say a 0% inelastic collision is going to be something like clay or silly putty. Drop it on the floor and it just goes like that, right? No rebound. Silly putty is not a good example because it works. So let's say clay, just a lump of wet clay. When it hits the ground, it just goes boom, right? The it loses all of its kinetic energy. But the energy, the total energy is conserved. Right? Conservation of energy is guaranteed. Either in a chemical reaction or in a physical process. The kinetic energy is conserved. The total energy is conserved, and the total energy is a combination of potential energy and kinetic energy. Equals total energy. So if you lose all the kinetic energy, it's converted into potential energy. And in that case, the potential energy is temperature. Right? When it smacks the floor, if you have a sensitive enough thermometer, you can measure an increase in temperature in the mass, either one of the objects, right? The floor or the clay.
I should remember that. I saw an experiment on where a guy cooked a chicken by slapping it.
Cooked it by slapping it.
Yeah, built a machine that would slap it like several times a second. And I don't think he actually cooked it, but like he did that and then measured how much the temperature increased. Like you have to hit it this many times in this amount of time. Okay.
I expect that if he cut open the part where the impact was, he would find coagulated meat. It would have started to cook. But since it's a large mass, it dissipates the temperature and it only cooks in a small area.
Yeah, I think it's something ridiculous. Like, yeah. I can't remember what it was, but it was a couple thousand revolutions a second.
Yeah.
And I guess he put multiple hands on like a spoke for something. It's like, well, okay.
You know, that sounds like something the government would be interested in financing. Give them a grant to do that. Right.
People, usually question, I understand science is cool and all, I like it. There's a limit.
So that was our last proposition. These are all, we assume that the collisions are elastic. Okay. Now, the reason we went to all this trouble, and I understand why the authors did it now, is we're trying to gain an understanding of phase changes in matter and interactions between different types of matter. And we're going to consider the kinetic energy a disruptive force. In other words, the more kinetic energy you have, the more likely you are to disrupt any interactions. And the potential energy is, what do they call it? Potential is cohesive force. So if we look at it in terms of this as a balance between these two, then we look first at the phase of the matter. Let's say kinetic and potential. All right, let's go with that. Okay, for solids, the cohesive forces dominate. We're trying to get an understanding of why things are solid, liquid, or gas. And the cohesive forces dominate, the disruptive forces are minor. Let's see. I'll leave that there. So for solids, we have cohesive versus disruptive. So the cohesive forces are large in a solid, and the disruptives are small. relative to one another. For liquids, see, I think I got that on another slide. Actually, the disruptive forces are small because all the solids can do, since they're locked into position, their molecules are locked, all they can do is vibrate. And so you can get some energy out of that, but not much. Well, if we keep adding energy to them, then we reach a point where they start to vibrate so much, the disruptive forces balance the cohesive forces. So in this case, they're equal, roughly equal in size, cohesive versus disruptive. They balance one another. There's enough cohesion to hold the molecules relative to one another in terms of their volume. The volume, if you take a solid and go to a liquid, the volume increases only slightly. They just need enough space to move past one another. That's why liquids require a container and solids don't. And the densities, generally speaking, the density of a liquid is going to be less than that of a solid. Not by a lot, but measurably less. There are exceptions. Oh, we're not finished talking about solids, sorry. Since the cohesive forces are strong, solids retain their shape. That's one of the main ideas. And because they're close to one another, and the idea of incompressibility in a solid is that there's not a lot of space between the molecules. In fact, they're usually touching. So in order to compress a solid, you would have to actually distort the molecules somehow. They have relatively high density compared to liquids and gases. I mentioned the small compressibility. If there is space between the molecules, then there is room for compression. You can take up that space by simply compressing. They generally have very small thermal expansion. It's measurable, but it's usually small compared to liquids and gases. As you increase the temperature, you increase the kinetic energy, the disruptive forces. And it's still a solid, right? They're small, but they're not as small. The disruptive forces are getting bigger as you increase the temperature. And that means they're tending to vibrate more, and they're pushing each other apart. Now we're at liquids. They're about the same magnitude, cohesive and disruptive forces. And what this, they're still packed close to one another. That's why the volume doesn't change much with the transition from solid to liquid. But they are in motion. And since they can't hold their shape, they've got enough energy, they've acquired enough energy from here to here, that now they can move past one another. They're not locked in position anymore. And because they're not locked in position, they have an indefinite shape. You have to put a liquid into some sort of container. Otherwise, it'll just spread, some more than others. They still have a relatively high density because all they've acquired is enough disruptive force that they can move past one another. But they're still not widely separated. Now, there's one exception to that, is water. When water goes from ice to liquid, then the density increases for the liquid. Whereas the solid is less dense than the liquid. And I mean, you can observe it. Just put an ice cube in water, and what does it do? If it were more dense, it would sink. It's less dense than water, so it floats. Not much, right? How much of an iceberg is below the surface and how much is above the surface? Yep, 10% above, 90 below. So it's only about a 10% difference in density between liquid water and ice. And the reason for that is that the ice, when it goes from liquid to solid, adds volume. And it adds volume with a definite crystal structure. It takes the water molecules and puts them into a hexagon. Right? So we would have, say, oxygen here and a hydrogen there and another hydrogen here. And that actually, we have another oxygen here, hydrogen here. Because I did that because these are not covalent bonds. These are covalent bonds, these are not. They're intermolecular attractions. And then we have another oxygen here and a hydrogen here. That. And what that does is, and of course, this has another hydrogen here. This one has another hydrogen here. What that does is it introduces all this space in that hexagon, and that causes the crystal structure to expand. And if you increase the volume, right, from our density calculation, increase the volume, density decreases. There's more to that story, but I don't want to take up all your time. Generally speaking, though, as we go from solid to liquid, the density decreases for most solids. There's still very little compressibility. It's liquids are compressible, but not much. They have a small thermal expansion. It's not much greater than solids, but it is measurable. And it's usually measurable in terms not of linear expansion, but of volume expansion. Gases. Gases. Flip this thing around. Cohesive forces in a gas are small, and disruptive forces are large. In other words, the particles in a gas have lots of kinetic energy. By comparison to liquids from which a gas is derived, the kinetic energy of the particles is massive. It's very large. That's the reason that it takes a certain amount of energy to melt a cube of ice. I mean, you put it in your hand and it'll melt. But you can't put the liquid water in your hand and turn it into a gas very fast. It takes a whole lot of energy to get it to go to a gas. The molar heat capacity, the molar heat of vaporization of water is huge compared to the molar heat of fusion, which is the amount it takes to melt ice. Because you've got to flip this thing around, make this small and this large by comparison. You know, these are relative terms. And for that reason, when we study gases, many of the studies conducted on gases, it doesn't matter what the gas is, because they don't interact. The molecules don't interact that much if the temperature is high enough. And that's good, because when we start studying gas laws, the gas laws apply to any gas. And that's the artist's idea. They're very widely spaced, lots of room, and they're moving really fast. And in my general chemistry class, we calculate in the second semester, we calculate the average velocity of gas molecules. And for air, right, the nitrogen and oxygen molecules, on average, are moving a little bit faster than the speed of sound, on average. And of course, if you decrease the mass of the particles and you're at the same temperature, they've got to have the same kinetic energy. So if the mass goes down, well, I erased it. If the mass decreases, then the velocity has to increase in order to keep this constant. So if you decrease the mass, say go from oxygen, nitrogen down to helium, then at the same temperature, the same kinetic energy, those molecules, well, atoms for helium, are going to be moving a lot faster. Probably 50% faster. Okay. So, as a consequence of the large disruptive forces and the molecules being widely separated, moving really fast, gases have an indefinite shape, but they also have an indefinite volume. In other words, if you put a gas into an evacuated container, it's going to expand, fill the container. Always. And as a side note, if you mix two gases together, they're going to form a perfectly homogeneous mixture every time. They make a solution without exception because there's lots of space between them and they're moving really fast. They can accommodate any number of other gases in that mixture. They have compared to the solid and liquid from which gas is derived, their density is very, very low because we've increased the volume to such an extent that the density goes way down. And they have very large compressibility. In other words, you compress a gas, it's just going to go like that because of all the space between the molecules. There's lots of room to remove from that mass of gas. We're just putting the molecules closer together is all we're doing. And they have a higher thermal expansion than solids or liquids. And actually, there's a law that speaks to that. It's called Charles' law. We'll get to that in just a minute or two. All right, gases, liquids, and solids. Now we go to the gas laws. We're going to take them in chronological order. Which law came first and why? The why is fairly simple. The gas laws were discovered and quantified, developed, were given life, so to speak, at a time when the technology permitted the measurements that were required to define the particular gas law. So these are generalizations. They're all mathematical expressions of how a gas behaves. And in order to understand the physical behavior of a gas, you only need 4 conditions, 4 parameters. You describe the pressure, the volume, the amount, that's my abbreviation for the number of moles, the amount, and the temperature. If you have a gas and you've measured the volume, the pressure, the volume, the amount of gas in it, the temperature, you've completely described that gas, not chemically speaking, but physically. And just as a reminder, a law simply says this is what happens. It makes no attempt to explain why. All right. So we're going to look at pressure and volume first. Volume was probably, I'd be willing to say it was the first measured property of matter that was easy to determine. If you have a regular shape, all you have to do is measure it in 3 dimensions and multiply them out, and you got the volume. Or if it's an irregular shape, you can submerge it in a liquid with which it doesn't react, of course, and measure the difference in volume. So volume came first. Then pressure. We needed a way to measure pressure. Right? Physically speaking, pressure is the force applied per unit area. That's its definition. But there are a number of ways of quantifying that value. And one of the ways was invented by an Italian, Evangelista Torricelli. Torricelli invented the barometer. And what he did was he took a vat of mercury. And in those days, let's see, when was that? During the Italian Renaissance. Late 1500s, I think, early 1600s. Technicians were very good at producing shapes of glass. They were good at working glass, and they could produce a tube of uniform diameter of any length you wanted. So I don't even know if he was a technician of that type, but he certainly had access to it. And all he had to do was seal off one end. And he took this glass tube, sealed at one end, and filled it with mercury till it was right at the top. Then he put his thumb over it, inverted it, and submerged his hand in the mercury and turned it loose. I didn't know about mercury poisoning. Of course, liquid mercury is not that bad, as long as you don't get it inside you. Organic mercury, yeah, that is deadly. Like dimethyl mercury will kill you slowly. It'll destroy your nervous system.
What is the difference?
The ability to penetrate the cell, right? Metals like this, even in gaseous phase, don't cross the cell barrier easily. The cells have defenses against that. But once you convert it into an organometallic compound, then it can move through the membrane into the cell. That's where it does its damage. Make it.
Oh, you have to make it.
Yeah.
Not.
It can occur in nature too. Once mercury gets loosed into, there are microbes that will convert it. Yeah. So mercury spills are not bad for the mercury itself at the beginning, but they are bad down the line when bacteria get hold of it and convert it into organic forms. Yeah, then it's really bad. So he got his tube with an open bottom here, right, and there. And when he turned it loose, the mercury dropped. So let's just say down to here. So this is all filled with mercury up here. As a side note, he produced the first vacuum. Because if there's something there, and then now there's nothing there, that's a vacuum. But he was interested in explaining why it didn't drop all the way down to the bottom. You know, I mean, logically, maybe you think it would, but it didn't. So he reasoned that there was a force being applied to this surface here that was being delivered through the liquid and holding that column up. It was a force great enough to hold it that high. And he reasoned properly that it was air pressure. So the pressure of the air, the column of air from the surface of the earth to whatever the limit of the atmosphere was at that moment, was enough to support that column of mercury, because it had nothing else pushing on it here or pulling on it, because that's a vacuum. So that was the barometer, and it was tested by, once he invented it, he and other scientists tried to put it to use. So some of them set it on their desktop and just watched it day after day after day, and they noticed it was going. They correlated that with good weather, bad weather. And we still do that today. Low pressure means bad weather. High pressure means good weather. And he also, they threw it in the back of an ox cart and go up the mountain. And when they got to the top of the mountain, they found it was at a lower level. So if you're higher in the atmosphere, there's not as much atmosphere above you to support the column, so it drops. And if you go down to the ocean, down to sea level or below sea level, you'll find that it'll go up, because now there's more atmosphere above you. So now we had a way to measure pressure. Now this was air pressure, but we also had a way to measure pressure of gases once you convert the barometer into a manometer. In order to do that, all you have to do is seal off that, and instead of air pressure, now you've got a connection to a sealed container of gas. Now the pressure inside that vessel is pushing down on that. Now, of course, when it does that, you've got to add air pressure to it, because when you sealed it off, it already had air pressure in it. Right? So the total pressure is the pressure of the gas plus the pressure of the atmosphere. And that's what this is measured. So if you subtract the pressure of the atmosphere, you can measure the pressure of the gas. So we had a barometer sitting on the table over here to measure the pressure of the atmosphere, and a manometer over here measuring the total pressure. And they did that in millimeters of mercury. So the distance from here to the top, or wherever it happened to be, is in millimeters of mercury. And later on, we honored Torricelli by saying millimeter of mercury equals a torr. Same thing. So if you, and it was also standardized so that we could interconvert units at 760 millimeters of mercury, of course, is equal to 760 torr. That's equal to 1 atmosphere, which is taken to be the average air pressure at sea level. So now we've got different units of measure that we can apply to pressures. And if we use this definition, then we can measure the pressure inside our tires as pounds per square inch, right? Force per unit area, PSI. And then we can equate this 1 atmosphere is also 14.69 PSI. I think this one says 14.7. It's rounded off. All right. Now, SI units for pressure would be kilograms per, actually, it's not kilograms. Kilogram is not a force, is it? Kilogram is a mass. A force is a Newton. Newton per square meter. 1 Newton per square meter is 1 Pascal. That's the SI unit for pressure, the Pascal. I need to change that slide. That's not right. SI units would not be kilograms per meter squared, it'd be newtons per meter squared. Okay. So if we go back to the kinetic molecular theory, what is causing this pressure? The gas, we learned, has very high disruptive forces. That means the molecules are moving very fast. And when they smack each other, they transfer energies. When they smack the walls of the container, they transfer energy. Right? So we can measure pressure with a gauge. Right? Let's say we have a gauge here. So the gas molecules are impacting the diaphragm and registering pressure, simply because the kinetic molecular theory is true. If it weren't true, we wouldn't be able to measure the pressure. Now, this is not a mercury barometer. The one I've drawn here is called an aneroid barometer. Aneroid means without liquid. And it's usually a diaphragm of some kind. Right, there's the barometer, a picture of a barometer. I've got one of these on one of the campuses at New River, hanging on the wall. And you don't want to move it unless you take special precautions. All right. So now we have a way to measure volume, we have a way to measure pressure. So along comes Boyle, Robert Boyle, who investigated the relationship between pressure and volume. He wanted to know, if we change the pressure, how does the volume change? Well, in order to do that, if you want to use, if these are your variables, these two must be constant. You can't let them vary either, because that would mess up your calculations, right? So for Boyle, these are constant. It's easy to make the number of moles constant. Right? You just trap the gas and don't put any more in and don't let any out. The temperature is relatively constant over the time frame of the experiment, because it only takes a few minutes. But if you wanted to let it go for hours, then you could stabilize the temperature with an ice bath. Right? Water and ice together is always 0 degrees Celsius. As long as you've got both solid and liquid there, you're going to have stable temperature. Anyway, what Boyle did was he took the barometer tube that was straight and bent it into a J. And sealed it at the short end. Okay. And then you'll never guess what he put in it. Mercury. Now, the reason that they used mercury was because of its density, right? It's like 13.5 times as dense as water. You could use water and do the experiment, but a barometer made with water instead of mercury would be 13.5 times taller than, right, the normal barometer, right? So you'd have to go 33 feet to get 1 atmosphere pressure measured, right? All scuba divers know that number. If you go down 33 feet, you've added an atmosphere of pressure to your body in the water. So what Robert Boyle did was he took mercury and he put it in the tube and it pooled up at the bottom. It's like that. He added some more, pooled up some more, added some more. And when it touched the inner wall there, that gas was sealed. Now this is constant. And then he kept adding it. And eventually he put maybe this much of mercury in there. Right? But this side only moved up that much. Now we know why that is at this point, because when you push those molecules closer together, they still got all the same kinetic energy, but there's more of them pushing on a smaller surface, right? It's the same surface moving up, but they're all impacting it with more. There are more impacts from a smaller volume with the same molecules at that temperature. So that increases the pressure here. So there's a difference between the pressure here, the difference between this and this. Let's see. Yeah, the difference in this mercury column. This is the measured pressure of mercury on that gas. And then there's also atmospheric pressure. So the total pressure on that gas is atmospheric plus the mercury column. That's why when we do our experiment, we need to know the barometric pressure. And then we're going to measure the pressure inside the container with tire gauge. And we have to add to that the atmospheric pressure to get the total pressure on the gas. So once he got this value, he just measured the volume, and these tubes are uniform diameter. So really all you need is the height. You could calculate the total volume if you wanted to, but for his purposes, all he needed was the height here, plus the height of the mercury here, plus the height of the mercury in his barometer. And he just set up a table, pressure and volume. Got data, a series of data points, which we're going to do also. And he multiplied those two together, pressure times volume. Right? And within experimental error, he got a constant value. So as the pressure goes up, the volume goes down. And that expression looks like this. Pressure times volume equals a constant. Okay? And within the experiment, it doesn't matter what units you use, as long as you're using the same units over time. It's only when you want to interconvert from one experiment to another where you have to standardize your units. All right. What they're showing you here is a modification of Boyle's law. And the way you get that is within this experiment, pressure times volume is a constant. So if we have one measurement here and one volume there, it's equal to a constant. And we proceed with the experiment. We measure it again. That's equal to the same constant. Okay. Remember that, let's see, what's that mathematical law? Is it cumulative? No. Distributive? If A is equal to B and B is equal to C, then A is equal to C. That's the one I'm trying to get at. So if this is equal to that and that's equal to that, then we just throw that out, right? Because they're both equal. So P1V1 equals P2V2. This type of expression is what I call before and after. If you know the conditions of a gas before and after, and one of them is unknown, then you can solve it. Right? Let's say we know these two before, and then we measure the volume after, we can calculate the pressure. All you need is one unknown in an algebraic expression, and you can solve it. Also, in any type of mathematical expression, if you have a product of variables equal to some constant, then these two variables are always inversely proportional to one another. In other words, as this one goes up, that one has to go down to keep this constant. So if you have a product equal to a constant, it's inversely proportional. And I'm going to show you direct proportion in a second. An experiment, a modern experiment, where you measure the pressure inside that container at 100 millimeters of mercury is 8 liters of volume, and then you go 200 millimeters of mercury. Pressure will occur if we decrease the volume to 4 liters. So the proportionality is linear. If you cut the volume in half, you increase the pressure by twice. So there's an expression for Boyle, and we can rearrange these. Right? We can put both pressures on one side, P1 over P2, and then V2 over V1. That would be the same expression, just rearranged. Okay. Here's another exercise. If we have a sample of helium gas measured at 12.4 liters and at a constant temperature of 23 degrees and 0.956 atmospheres, what volume will it occupy at 1.2 atmospheres? We increase the pressure, we can estimate or surmise that if we increase the pressure, the volume is going to go down. So it'll be less than 12.4. But we can actually quantify it. We just put those values into our expression. And when you're faced with a problem like that, it's important to put those values in the right place. So I usually set up a table, P1, V1, P2, V2, and extract those values from the problem, right? P1 is 0.956 atmospheres. V1 is 12.4 liters. P2 is 1.20 atmospheres. And this is our unknown. So if you do it that way, then you can plug it into your formula without making an error. If you jumble these up, which is likely to happen if you try to extract it from the problem and bring it over to the formula, then you got a 50-50 chance of getting it wrong. And as expected, the volume did go down. And notice that this is a ratio, right? When I put P1 over P2 equals V2 over V1, those units of measure, as long as they're the same for both pressures and the same for both volumes, then you can use any expression you want because the units cancel. Okay. Next law is Charles' law. Charles was a Frenchie. He came along about a century after Boyle. Now, for this experiment, he wanted to know the relationship between volume and temperature. Let those two be the variables. That means this one has to be constant and this one has to be constant. Pressure and moles. And historically speaking, the reason that this one came after Boyle was because up to that point, they had no reliable way to measure temperature. They had various proposed ways. I used to have a what did they call it? It was a, shoot, was a name for it. You've seen these, tubes with the little, bulbs in them and temperature things dangling down from each one. And they, as the temperature of the solution changes, the density changes and they float. So the last one to float, just before it floats at the top, that's your temperature. Actually, the bottom one of the floaties, that's your temperature. It's based upon Archimedes' principle, I think. Anyway, that's okay if you're looking for temperature differences of 2, 5, or 10 degrees, but we want tenths of a degree. And we had to wait until the thermometer was invented. And when that happened, then scientists could investigate the relationship between volume and temperature. And what Charles discovered was that as the temperature increased of a gas, the volume increased. And the expression of that is volume related to temperature this way is a constant. So here's our direct proportion. As temperature goes up, volume goes up. And that is the expression of a quotient, not a product. So a quotient says that if it's going to be constant, if temperature goes up, volume must go up, mathematically speaking, in order to keep that constant. And we do the same thing here as we did with boil, right? If it's equal to that constant, then we can get rid of the constant. And this is our before and after expression. V1 over T1 equals V2 over T2. Now, there's one other stipulation. In order for this to work, the signs of the temperature must always be positive. You can't have a negative. If you have a negative, that throws everything off, right? For obvious reasons. So that's why Charles had to convert his temperatures. Well, actually, if we want to use this law, the temperature has to be in Kelvin for our purposes, because Kelvin is always a positive number, right? 0 Kelvin is absolute zero, nothing below it. So they're always positive. When Charles did his experiment, he was working in Celsius. So all he had to do was plot his data. As temperature goes up, volume goes up. And he established the relationship there. But if you're going to use this formula, we have to use Kelvin. And in fact, I think Kelvin, well, I've got Kelvin's original paper, a copy of it anyway. And he used a thermodynamic reasoning, right? It was popular at the time. But we can also get an idea of how he worked his temperature scale. He just said, what would happen if the volume of the gas dropped to 0? And an ideal gas would always be a gas all the way down to absolute 0. So if this temperature scale is Celsius, then his temperature scale, Kelvin, would set this one at 0, and where it intersected the x-axis is 0 Kelvin, but it's also minus 273 degrees C. So that means 0 Celsius is 273 K. That's why if you want to calculate K, you just take C plus 273. So whenever we're working these gas laws, temperature is, we have to always convert it to Kelvin. And that gives us a direct proportion. As the temperature goes up, volume goes up. All right. So here's an example where we have a word problem. And what have I always said about word problems? They're designed to confuse. Word problems are not your best friend. So let's say a balloon contains 1.3 liters of air at 24.7 degrees, placed in a beaker containing liquid nitrogen. Actually, that might be the atmosphere above liquid nitrogen, but that's not liquid nitrogen. Liquid nitrogen is minus 195 degrees C. So that would either be in the atmosphere above nitrogen or that's dry ice. I think that's what it is. Anyway, we're cooling it down. So the first volume, first temperature, second volume, second temperature. What goes where? Initially, we have 1.3 liters at a temperature of 24.7 degrees C. We're going to have to convert that to Kelvin. Okay. And the second volume is the question. At this new temperature, minus 78.5 plus 273. Now we have everything in its proper place. We can plug it into the formula. Now you can either plug it in and solve for the unknown, or you can solve for the unknown and then plug it into the plug values into the knowns. But we end up with a shrinkage. Right? We go down in temperature, we get a shrinkage from 1.3 liters down to 0.89 liters. All right. Let's see. We left one out. Let's see. Boyle, Charles. Let's see, did I put it in here? No, I didn't. All right. So I'm going to give it to you now. Because this one is very, very important. I'm not sure why your authors left it out. I should modify the slides to include it. Is Avogadro's law. Avogadro wanted to know the relationship between volume and moles. So those are his variables, and these are constant. By the way, we didn't mention how did Charles and how would Avogadro maintain a constant pressure in on that gas. I can envision one way, a cylinder of uniform diameter and a piston in here with put some mass on it like 1 kilogram. Okay. So the pressure is constant and the piston is allowed to go up and down at that constant pressure. So whatever we do in here, the volume will change. Now for Charles, what he did was he left the gas alone in here, moles constant, and just changed the temperature. But for Avogadro, he had a valve in here to a source of gas. And he put a known amount of gas in there. And he was able to equate the moles, the amount of gas going in increments. So he was able to measure what happened when you put more moles in the container and the volume increased. So Avogadro's law then would be volume moles equals a constant. And then if we expand it the way we did before, we get rid of the constant. Before and after is V1 over N1 equals V2 over N2. So that would be Avogadro's law. Now, that's one expression for it. Actually, the more important interpretation of Avogadro's law was published by a student of his. If I can remember how to paint myself into a corner. I think it's two N's. Cannizzaro, don't hold me to that. But he took Avogadro's work and used the concept. And what Avogadro actually said was, if you have two gases, it doesn't matter, they don't have to be the same gas. Two gases in two separate containers, and they're the same volume. Exactly the same volume. They're also at the same temperature. And they're at the same pressure. If all of these three are constant, they're the same for both of them, then this one must be true. The number of particles, the moles of particles in this one equals the number in this one for gases. Now, the significance of that was that now we have a way of proportioning the masses of individual molecules and atoms. Because before this, chemists were more like chefs, right? They cookbook their experiments based on mass. And when the experiment went wrong, they didn't know how to correct it because they didn't understand properly what was going on was not mass interaction, but particle interactions. So now we know individual particles, these are exactly the same. Then we know that the difference in masses, mass 1 is not equal to mass 2. If they're different gases, it's more likely that's true. The difference in these two masses is due to the difference in masses of individual particles. So now we had a way to, to figure out how many particles were in a given mass of that element or compound. And that eventually led to periodic table. In fact, Mendeleev credited Avogadro and Cannizzaro for helping him understand the organization of his table. He credited them in his publication. Okay. Now that we have these three laws, suppose instead of holding two constant and letting two vary, suppose we have a situation where two or more, actually three or even four conditions are allowed to vary. Maybe in real life, we don't have a way to control them. So we need a way to investigate. Well, now we come to the combined gas law. We're going to start with Boyle's law. So we know that P1 times V1 equals P2 times V2. Then Charles said that volume and temperature were related like this. Like volume and temperature. If pressure is held constant, then we get Charles' law. Okay? And then if we introduce Avogadro's law, volume and moles. Oops, it's a 2. There we go. So if we hold any two of these constant, like if we hold pressure and temperature constant, we get Avogadro's law. Or if we hold, well, we already did Boyle's and Charles. So this is actually P1 V1 over T1 is an incomplete combined gas law. This is the complete version. Here. All right. So in this situation, we have at what temperature does 121 milliliters of CO2 at 27 degrees and 1.05 atmospheres occupy a volume of 293 milliliters? at a pressure of 1.4. So first of all, do we need all of these variables? No, because this gas is trapped. This value is constant, right? So it drops out of the expression. And now we need to find these values. So what's the first pressure? 1.05 atmosphere. And the first volume, 121 milliliters. And the first temperature, 27 degrees. 27 plus 273. And let's see. 293 milliliters here. So our units of volume are the same. That's good. And 1.40 atmospheres. Our units of pressure are the same. That means that the temperature is going to be given to us in K. Right? So we get a K value of 969 K. And if we want it in Celsius, we have to subtract 273 from that. And when we do, we get 696 degrees Celsius. There we had 3 variables. And only one of them was unknown, of course, otherwise we couldn't solve it. Right? Remember algebra? How do you solve an equation in 2 unknowns? You need 2 equations, right? 2 equations with the 2 unknowns, simultaneous equations. Then you can solve it. We're not going to do those. We're only going to do 1 unknown. Okay. So that's what you do. And up to this point, we've had before and after. What are the conditions before? What are the conditions after with 1 of them unknown? Now we're going to look at a situation. Say we don't know what the before is. We only know what the state of the current system is. So now we're going from before and after problem solutions to state solutions. What is the state of the system right now? Answer the question. In order to do that, we need to use the combined gas law, P1, V1 over N1, T1 is equal to that other expression, or it's actually equal to a constant, right? Because of the way we created the before and after situation with the gas laws, they were equal to a constant that's equal to the other expression. Now we're just going to throw that other expression out and bring back the constant. So P1 V1 over N1 T1 is a constant. Well, if we know what we want to know is what is that constant under a given situation. So if we say, all right, let's use SI units. What's the standard SI unit for volume? Is the liter. For the temperature would be K. For this is moles. And for pressure we're going to use atmospheres. Now, atmospheres is not the SI unit, but we're going to use atmospheres anyway. If we know those units, then all we need is what's the magnitude that goes with each unit. So standard temperature and pressure for gases, for our gas laws, standard temperature is 0 degrees C plus 273 equals 273 K. So this one is 273. Right? And pressure standard is 1 atmosphere. So this is 1 atmosphere. Okay. And standard number of moles, of course, is 1. So what we need to know is at that temperature, with that many moles of gas, at that pressure, what's the volume? And the volume was measured. Measured volume is 22.4 liters. So now we have values in these units, moles, K, liters, and atmospheres. As long as those units are the same, then we can calculate this K. 0.08206. And remember, when you divide numbers, you also divide the units. So the units of this value are liter atmospheres per mole K. And this is given a special symbol R. This is the ideal gas constant with these units, liter atmospheres mole K. Now, there are a whole host of different R values, but their units of measure change. So if you change the units of measure, you change that value also. And this is the one we're going to use. So if you're going to solve this problem, you got to be sure that your units are in liters, atmospheres, mole, and K. And if you do that, then this expression, PV over NT equals R, and we usually rearrange it so it's linear, all in the numerator. So PV equals NRT. That's the way you'll usually see it. All right. So here's a situation when you look at a word problem and you're trying to figure out whether you can use one of the gas laws or the combined equation versus the ideal gas equation. Look to see, are you given before and after conditions? If you're not, then you have to go to this one. So in this case, an automobile tire at 23 degrees C with an internal volume of 25 liters is filled with air to a total pressure of 2.18 atmospheres. What's the number of moles of air in that? Right? We're not given before and after at all. We're not given 2 temperatures. We're not given 2 volumes. We're not given 2 pressures. We're only given 1. So we have to go to this one and be sure that all of the units are compatible with this constant. And if we do, right, we put in atmospheres and liters on this side, and we put our unknown is moles, and then we put in, I use 08206, and for some reason this one has 0821. And then the temperature has to be converted to K. And if you do that, you can calculate the number of moles at that state, at that particular time, with only those values. Let's see, what's the pressure in a 304 liter tank that contains 5.670 kilograms of helium at 25 degrees C? All right, in this case, you've got liters, you've got degrees C that has to be converted to K, and you've got kilograms of helium that must be converted to moles in order to determine the pressure. Because this will be your unknown. You need to convert kilograms to moles. That's a constant. Temperature needs to be K, and the volume is given in liters. And if you make those conversions and solve for P, right, this expression right here converts to moles of helium. In other words, that's in one step, 5.670 kilograms. If you do dimensional analysis, you want to convert it to grams first. Right, kilograms, 1,000 grams. Right. Then you can convert grams to moles. And you need 4.003. Go. And that's what they did. That gives you that expression to convert to moles. And that goes in this position. then you put R in, then you change the temperature to Kelvin, and you put in the volume, solve for P. And it's 114 atmospheres. That's a lot. That is massive pressure in that tank. If you multiply that by PSI, like 14 times 100 it'd be like 1,500 PSI in that tank. That's why pressurized gases are so dangerous. You don't want to drop a tank. Okay, Dalton's law of partial pressures. Now we know how to solve before and after problems. We know how to solve state problems of gases. Now we want to add to our repertoire the ability to solve problems with mixtures of gases. And that's where Dalton's law of partial pressure comes in. It's very simple. John Dalton, this was the same the same John Dalton that proposed the kinetic molecular theory of gases. No, excuse me, the atomic theory. He proposed the atomic theory. And he also proposed this gas law, the Dalton's law of partial pressure. Okay. All he said was that the total pressure measured in a mixture of gases is due to the mathematical sum of the pressures of each of the individual gases. Up to however many you have. Very simple. All right, so if you have like the red balls, you have pressure of 1, and the blue balls, you have pressure of 3, and the green ones, you have a pressure of 2. Then when you add them all together, you get a total pressure of 6. If you mix them together, you get a total pressure of 6. Let's see. This problem says if you have oxygen, helium, and nitrogen, a total pressure of 780 millimeters. So we're given this 780 millimeters of mercury is the total pressure of that gas mixture. What's the partial pressure of oxygen? So the pressure of oxygen, if the pressure of helium and nitrogen are 86 and 124 respectively. So the pressure of helium is 86 millimeters of mercury, and the pressure of nitrogen is 124 millimeters of mercury. Well, that's simple. You just subtract these two from that one and you get the pressure of oxygen. See if I can estimate that. That's about 200, it's about 580, 570. So it should be D. $11:00. How are we doing? Okay. We're in lab time now. All right. So here's an interesting problem. I'm going to leave those up there for now. Say we have 2 bulbs filled with gas, and there's a valve in between them. Let's see, the one on the right is smaller, yes. Okay. And the one on the left has an internal pressure of 2 atmospheres and a volume of 9 liters, 9 liters. And the one on the right has 3 atmospheres pressure and 3 liters of volume. Question is, when you open that valve, what will be the final pressure? Okay. what we want to do is separate those two bulbs in our mind into two separate experiments. Consider this bulb is the way it is, and the right bulb is evacuated. There's nothing over there. So what would be the pressure if we allowed this gas to flow into that space and equalize? And then go the other direction. Let this one be the vacuum and let that one expand into it. What would be the pressure due to this gas? And that's the pressure of this gas in that new volume. The pressure of the gas of this one in that new volume, the total pressure is going to be the sum of both of them. Okay? So we actually use two laws. We use Boyle's law, once for this one, once for that one, and Dalton's law to get the final answer. Okay. So the final volume for both of them is going to be 12 liters, right? 9 plus 3. The initial volume for the left-hand side, of course, is going to be 9. The initial pressure is 2 atmospheres. That gives us a before and after Boyle's law for the left-hand cylinder with a pressure as an unknown. All right, so there's our gas 1 on the left. We solve for the final volume, final pressure, and we get 1.5 atmospheres from 2. So that makes sense. I mean, if it goes from 2 atmospheres into a vacuum, it's going to drop in pressure. Only we've quantified it. And we do the same thing for the right-hand side. Okay, that's square. If you change the fonts, sometimes what I want it to be a dot or an X times P times V, it shows up as a box because the font's not in this version of PowerPoint, and it doesn't know what to do with it. So it just puts a box there. So now we have 3 atmospheres to begin with out of 3 liters going into 12 liters, and that gives us 0.75 atmospheres. So now we use Dalton's law, add them together. And the final pressure would be 2.25 atmospheres. And you can confirm it, right? Just do the experiment, measure the pressure, it'll be 2.25 atmospheres. All right. The reason I have this in there is sometimes I use this slide set and we have to pause and wait for the next to get it, but we're going to finish it. We're going to move on. Now we're going to talk about changes of state. We got all our gas laws. Now we're going to change states. And a change of state is simply a change of physical solid, liquid, or gas. Right? There's no chemistry involved there. Usually it involves heating or cooling. Sometimes, especially with gases, it involves pressure. Now, if you cool and squeeze a gas, you can turn it into a liquid easier. You should be able to turn it into a liquid simply by temperature, but it's easier if you pressurize it too. So when we have a change of states, I like to put them in this way. Let's say we have solid here, we have liquid here, and we have gas here. We can go from a solid to a liquid. We can go from a liquid to a gas. And actually, we can go from a gas to a solid. Okay. Solid to a liquid is called melting. Liquid to a gas is called vaporization or evaporation. Actually, if you heat it to where it's boiling, sometimes we'll refer to it as boiling. But that's a special case. Evaporation covers a lot more conditions. And then a gas to a solid is deposition. Okay. Now, if we go the other direction, say we go this way, solid to a gas is called sublimation. Okay. Think dry ice, going from a solid to a gas. A gas to a liquid is called condensation. And a liquid to a solid is called, what term they use? Freezing. Freezing. Okay. Those are the 6 possibilities for phase changes. I like my diagram better. Except they also include whether or not heat must be absorbed or released in order to make the transition. So when you're going from, and let's put it this way, exothermic is heat released. In other words, you can sense the temperature increase. And endothermic is heat absorbed. So it gets colder. So if a solid melts, it has to absorb energy. Right? Heat is absorbed, it's an endothermic process. So the freezing would be just the opposite. It'd be exothermic. So if something freezes, it has to give up energy in order to go from a liquid to a solid. You have to go? Okay. Sublimation, we're going from a solid to a gas, it has to absorb energy, which is endothermic. And deposition would be the opposite, the exothermic. And then if it condenses, goes from a gas to a liquid, it must, let's see, gas to a liquid, it has to give up energy. So that's exothermic. And evaporation, we have to add energy to a liquid to make it into a gas, is endothermic. Okay. These terms are always in reference to the system. In other words, if our system is, say, water, a certain mass of water, that's our system. And whatever happens, whether heat goes in or heat goes out, that's where these terms come from. If heat goes out, heat is leaving the system, it's exothermic. Heat goes in, it's endothermic. Oh, I got slides here. I should have looked ahead. So melting, sublimation, and evaporation are all endothermic processes. Endo. And exothermic processes are freezing, condensation, and deposition. All right. So when you get a liquid evaporating, you've got to break any attraction that is felt among the molecules. And that means energy has to go in. They have to gain enough kinetic energy to overcome any attractive forces. And remember, with the liquids, the disruptive and the cohesive forces are about balanced. So we've got to increase the disruptive forces so they can completely overwhelm the Disruptive forces completely overwhelm the cohesive forces. Yeah, I think I need to take a second and refill my drink. Go. So in terms of the kinetic molecular theory, we have to increase the temperature to the point that the molecules are moving so fast that they can't hold themselves together in the liquid state. Now, these processes can be viewed in two different ways. One is where do we start and what's the end result? We don't care what happens in between. What happens in between is how fast does it go? So for evaporation of liquids, the rate of evaporation is increased as the temperature increases. So we can evaporate faster if we increase the temperature to a higher point. That means there's more energy available. So as the liquid evaporates, right, it is an endothermic process. Heat has to be added to it. So if we bring it to a certain temperature and then we let it evaporate, the temperature is actually going to drop because the molecules that escape the surface first are the ones with the highest kinetic energy. Remember, temperature is average kinetic energy. You can have, if we diagrammed it, right, this is like temperature, and this is numbers of molecules. You actually have sort of a bell-shaped curve. That most of them will be in this range, but some of them will be out here, and these are the ones. Oh, that's not right. I got that backwards. Excuse me. My story's going to fall apart. Numbers of molecules here and temperature here. So if the temperature is past a certain point, they have enough kinetic energy to leave the surface, right? And as they do, right, those are gone. Now the average kinetic energy only has this temperature to deal with. So the overall temperature decreases. And that's referred to as a vapor. The liquid turns into a vapor. All right. Now, what we also notice is if we enclose a liquid in a container like this, in an Erlenmeyer flask, stopper it, then initially there are no liquid molecules in the space above. They're just air molecules. So everything is one way in the beginning. We have liquid here, and we have gas molecules. And in the beginning, they're all going one way at the very beginning. But eventually, you get enough in this space, and the temperature is dropped for both of them. You start getting return. So evaporation is one way in the beginning, but then you start getting condensation. And when the rates of those two are equal, the level of the liquid stops decreasing. And from our perspective, macroscopically, it looks like nothing's happening. But on the molecular level, the activity is furious, right? Their molecules leaving the surface and returning at the same rate. And what we find up here in this stoppered space is after we get enough of these molecules up here, we start getting returned, and the level of the liquid has dropped, and it doesn't drop anymore. We find now that what this is the vapor pressure for that particular compound or element. That's the vapor pressure at whatever the temperature is. If we change the temperature, then we add more kinetic energy to the liquid and we increase the vapor pressure. At this point, we have what's called the physical equilibrium. Because the processes are only physical, just phase changes. And the vapor pressure is constant at any given temperature. So it can be measured, it can be put in a table, right? If you have water in a container and you know the temperature, then you can look up in a table and tell you exactly what the vapor pressure is for water. Now, if you have a mixture of gases in there, say you've collected a gas by bubbling it through water into a container. It's picked up water vapor. So its pressure, along with the trapped gas, is going to be, those two together are going to be the total pressure. If you know the temperature, then you can tell what the vapor pressure of water is in that container, subtract that out. Now you know what the temperature of the dry gas is. And we've done that. I mean, I've done it before. When you have a chemical reaction and you want to catch one of the products is a gas, right? You just bubble it through water into a graduated cylinder that's inverted and filled with water. And then it displaces the volume of water with gas, and you can measure the total volume. And then you can measure the pressure. The total pressure is going to be atmospheric. And then if you know the pressure of water, you subtract it from the atmospheric pressure, and that's the pressure of the gas inside. Okay. Now what we notice is that this vapor pressure is constant for a given temperature, but only for given compounds. So as you change the compound, it's going to have a different vapor pressure. And it all depends on what are the attractive forces of the molecules for one another in the liquid phase. If there's strong attraction like water, I remember water is a polar compound. It's got a dipole moment that direction. Right? So it's going to be negative here, it's going to be positive there. Then water molecules have very strong attraction for one another. So at any given temperature, it's going to be a very relatively low vapor pressure. And if you have, this is hydrogen, we haven't talked about hydrogen bonding, have we? No. Anyway, if you have a compound that's say ethanol, right? So you have the OH here and the OH there. This is also going to be slightly positive and slightly negative. So that makes ethanol not as strong as forces of water, but relatively strong, and its vapor pressure will be moderate. But if you take that same formula, which would be C2H6O3, and change the structure. Right, this is the molecular formula, but the structure is different. Let's say let's change the structure to this one. Put the oxygen in the middle. Now we have dimethyl ether. This vapor pressure is going to be huge at the same temperature because the attractive forces here, it's a symmetrical molecule. It doesn't have the dipole to give you a stronger attraction. So this is going to be a low vapor pressure, this will be moderate, and this will be very high. So volatile substances like dimethyl ether are going to have very high vapor pressures at a given temperature, room temperature, for instance. So when the EPA or OSHA issues regulations and say you can only have so much of VOCs in your product, like paint, volatile organic compounds, they do it because the compounds that are used in many mixtures are volatile, very volatile. And you in a closed space, you can get a concentration that's high enough to cause problems. All right. So boiling is a special case of evaporation. When a liquid boils, it is evaporating liquid into gas at a vapor pressure of 1 atmosphere. Now, excuse me, that's standard vapor pressure, 1 atmosphere. Boiling can happen at any pressure, external pressure. But if you decrease the external pressure, you decrease the temperature at which it will boil. So if we say at sea level, it's going to be a standard temperature of boiling point. For water, it'll be 100 degrees Celsius at 1 atmosphere pressure. That's the boiling point of water. And it'll boil at that temperature. But if we go to Denver, which is a mile high, then the temperature at which water will boil will go down because there's less external pressure limiting the evaporation of molecules. And if you go to the top of Mount Everest, I think the boiling point would be like 75 or 78 degrees C instead of 100. You've decreased the external pressure so far that it would be difficult to boil an egg at that altitude. And even in Denver, it takes you 4 minutes for a 3-minute egg. So there's what boiling looks like in a green liquid. I don't know what that green liquid is. Probably food coloring. Now, there is a difference. I don't know if I made that clear, but boiling point is one thing. Normal boiling point is the temperature at which a liquid boils if the external pressure is 1 atmosphere. That's what we mean by normal boiling point. All right. Oh, good. There it is. I was off by quite a bit. The top of Mount Everest boiling point is 70 degrees. And let's see, do they have, no, they don't have Denver. They got Salt Lake City, which is not quite a mile, 96 degrees. Leadville, Colorado, it's 2 miles high, 89 degrees. Death Valley, boiling temperature of water is higher. And at the Dead Sea, it's probably even higher than that. All right. What's the vapor pressure of water at 100 degrees if boiling? 1 atmosphere. All right. I mentioned, as we went along, intermolecular forces. So we need to define terms here. soon as I finish erasing the board. You get two types of forces when we build molecules. One is intramolecular forces. The other is intermolecular forces. The intramolecular forces we normally call bonds, chemical bonds. And for our purposes of discussing intermolecular versus intra, we're going to focus on covalent bonds in particular. The intermolecular forces, these are the ones that occur inside the molecule. That's what holds the molecule together. Intra means within. Inter means between. So these are attractive, actually attractive or repulsive. Between molecules. There we go. Okay. Before we talk about the types of bonds, classifying the intermolecular forces, I want to make this one point. The strength of each relative to one another. The intramolecular bonds are always stronger than the intermolecular bonds. They have to be. I mean, logic tells you that if the intermolecular forces between molecules were stronger than the intramolecular bonds, they just rip the molecule apart. Right? It wouldn't stand a chance. So these have to be stronger than these. Right. Now that we know that, there are different types of interactions, intermolecular forces that can occur. Let me see. Let's see what kind of explanation they're giving. Okay, I do have a slide in that. That's good. Okay. This is just a list of them. Dipole interactions. Think of magnet. Like, North pole attracts South pole. Only with molecules, it's based on electrons. Hydrogen bonding is a special type of dipole. So we'll tease that out in a minute. London dispersion forces, and these are in the order of, actually they're not in order of strength. Hydrogen bond is the strongest of the dipole interactions. And then there are others. And then the weaker forces are London dispersion forces. I'll have to define those to you. You can also get interactions between ions, right? Positive and negative ions, or you can get interactions between ions and dipoles. So we'll cover those one at a time. The dipole-dipole interaction requires that a molecule have a partial charge, not a complete charge. A complete charge means ion. That is, electrons are transferred from one atom to another. In a dipole-dipole, what you get is an uneven distribution in a covalent bond. So for water's a good example. You got a covalent bond here with a hydrogen, and covalent bond here with another hydrogen. The strength of pull for electrons is stronger for the oxygen than it is for the hydrogen. Oxygen pulls on electrons stronger, so we get an accumulation within this shared bond. We get an accumulation of electrons over time closer to the oxygen, which gives it a slight negative charge. And that depletes the hydrogens. So I use that Greek letter delta, the little d, to mean partial. It's not a complete charge. If it were a complete charge, then there wouldn't be that bond. It'd be gone. And the only thing holding it together then would be Coulombic forces, positive, negative charges. But once we get this distribution, redistribution of electron density, now in pure water, what happens is if an oxygen approaches an oxygen side for the molecule, they'll repel one another. So the only way they can attract is if the oxygen approaches a hydrogen with its negative. And here, positive. So then you get an attractive force between them. That's a dipole-dipole interaction. Now with big molecules, you can get that type of interaction within the molecule. I mean, that's what holds the DNA double helix together. Right? It's two covalently bound single strands that wrap around each other in that double helix. And the interaction between the helices is dipole-dipole interaction. And that's a good thing, because when the cell goes to read the DNA to transcribe it, it has to open that molecule up in order to read the sequence. So the greater the polarity of the molecule, the stronger the dipole-dipoles. So here's an example with fluorine and chlorine. Fluorine has the strongest attraction for electrons, so it's going to be the negative side. Chlorine has the weaker attraction, so it's going to be the positive side. And then you get an interaction between the positives and the negatives. Now they show positive and negative signs there, but what they mean is partial. They should have put a delta in there along with it. The hydrogen bond is a special kind of dipole-dipole. And in order to have a hydrogen bond, you need hydrogen, obviously, and hydrogen has to be bound to either oxygen or nitrogen or fluorine. And the reason for that is these two things. These atoms are strong attractors for electrons, and they produce a very polar bond. And with the hydrogen in there, the hydrogen is very small. Right? It's just one proton. So it means it doesn't take up a lot of space. That means this oxygen can move really close and get closer. And the strength of attraction between charges, based on Coulomb's law, is stronger the closer you get. The force of attraction. In fact, the force of attraction is equal to Coulomb's constant and times the distance between the two. Excuse me. No, excuse me. Not right. Times the that's the wrong. There's a constant in there. I can't remember what it is. Charge on one and charge on the second. And then the distance between the two squared. So the closer they get, the stronger the force. And since hydrogen is so small, they can get really close together. Right? These two can approach very close. And it's a very strong bond. Intermolecular bond. Not as strong. It's not as strong as this bond, but it's the strongest of the dipole-dipoles. And the term I was looking for, I couldn't remember, was electronegativity. Electronegativity is a measure of the strength of attraction for electrons of an atom in a covalent bond. And the strongest of those is fluorine. Right? On the Pauling scale, fluorine is number 4. And then nitrogen and oxygen are less than that. But they're still pretty strong. And this slide tells you what I just told you about the size and the attraction between the two. Size of the hydrogen atom means that they can approach very close. There's an example. There's what water looks like. And that's why the vapor pressure of water is so low, because the strength of attraction keeps those water molecules in the liquid state unless you put enough energy into them. So if it were not for the hydrogen bonding, water would boil at some temperature less than 0 degrees Celsius. Which is the case for the analog, right? OH2, H2O or H2S versus H2O, right? They're in the same family, but sulfur doesn't produce the dipole strength that water does. So sulfur hydrogen sulfide is a gas at room temperature, whereas water is a liquid. All right, I already mentioned that one. Oh, I forgot I had this one in here. So the boiling point of hydrogen sulfide at 1 atmosphere is minus 60 degrees Celsius. We would expect, if it followed the trend in the family, right, tellurium, selenium, sulfur, oxygen, in that family, the dihydrides, water should boil at minus 80 degrees, but it doesn't. It boils at 100. And the explanation for that is the hydrogen bond. Now, the dipole-dipole interactions, the hydrogen bonds, and the ion dipole interactions, which you would see with, say, add table salt to water. Then you would get a dipole from water interacting with an ion like sodium or chlorine. Those are relatively strong on the intermolecular scale. Weaker forces that, let me back up and say again, nature just does what it does. It's our job to explain why it does what it does. And that's what London dispersion forces are designed to explain why, for instance, nitrogen gas condenses into a liquid if you get it cold enough and compress it, right? Nitrogen, if we look at the molecular structure, it's just like that. It's a symmetrical molecule. It has no dipole at all. So how does it generate forces that hold it together? We have to have cohesive forces in order to make a liquid. So where are they coming from? Right? They're not coming from dipoles. So that's where London, I think that was his last name, devised an answer. He said, whereas dipoles are permanent in the molecule. Once they're there, they stay there until the molecule is disrupted. Whereas London forces are temporary. So when a nitrogen approaches another nitrogen, instantaneously, electrons are always in motion, always moving. Instantaneously, we could get a partial redistribution like that in this nitrogen molecule, just for an instant, a microsecond. When it does that, this negative attracts electrons, repels electrons from this side, and this attracts electrons from that side. And for that instant, you get a positive and negative interaction. Now, these London dispersion forces are always happening, always, with any molecules. The reason we don't see them prominently in dipole molecules is that the dipole is so much stronger, it just swamps the London forces. It's only in molecules that don't have any dipole that we actually see the London dispersion forces at work. And this will occur with molecules like that, nonpolar molecules. It'll occur with noble gases. Right? This series, right? Neon, argon, yeah, argon, krypton, xenon. That's far enough. What we see is an increase in size. Size increases as we go down. Size contributes to uneven distribution of electrons. So the bigger the molecule, the bigger the atom, the more chance it has for instantaneous redistribution of electron density unbalanced in the atom. So we see that the chances for for London dispersion forces are higher for xenon than they are for krypton, and higher for krypton than argon, higher for argon than neon. And we see that in their boiling points. The boiling points, actually, boiling point, as the size increases, the boiling point increases along with it. Oh, good. I forgot I had the chart. So you'll notice that helium boils at minus 269 degrees C. What is that, Kelvin? 273, 269. That's 4K. The boiling point of helium is 4K. In fact, that is the coldest bulk substance that we can create. Liquid helium. It's only 4 degrees above absolute zero. It's weird stuff. You know what a dewar is? It's like a thermos bottle. It's a big beaker-shaped thing, only it's got a vacuum in between, and it's silvered to prevent transfer of heat in and out. So if you put liquid helium in that dewar, I've seen this done. It's weird. Helium will actually climb the walls and spill out onto the floor, the liquid helium. It has attractive forces for the glass, apparently. Oh, yeah, but it's not that cold.
Oh, okay.
Yeah, I mean, it's very cold, but it's not as cold as helium. Yeah, that's one of the problems with building rockets with liquid oxygen, liquid hydrogen as the fuel and oxidizer, is keeping those things cold enough so they store them in the tank. And you'll see once they fill up a rocket, you'll see it gassing off. That's because if they don't gas it off, the tank will explode. It has to have a relief valve. So they fill the tanks right before liftoff. And some systems use pressurized inert gas to drive the fuel and the oxidizer together into the engine. And I think Musk is using a process where the vaporizing gas is used to pressurize the cylinders so that it'll drive the fuel and the oxidizer together in the engine. Only he's not using hydrogen, he's using methane, liquid methane. That's easier to control because it has a higher boiling point than hydrogen.
I was confused for a minute. I know that's what they use for rockets. How do they get enough in there if they just got to use gas instead of liquid?
If they had to use gas, the weight of the cylinder would keep it on the ground. Right. Yeah. So they liquefy it, and they only turn it into a gas when it goes into the engine. And if you see the bell of a rocket engine, they'll usually have tubing around the bell. They run the liquid through that tubing. It's turned into a gas by the heat of the engine before it goes into the combustion chamber. That's how they convert it into a. If they didn't do that, then the valves would freeze up. They get so cold that they wouldn't operate anymore. And the turbine that pressurizes everything, it just all freeze up. They have to run the liquid through the bell so that it will turn into a gas efficiently before it goes into the engine. Okay, so that's an illustration of London dispersion forces for an element. Molecules show it too. They're the halogens, right? The bromine, dibromine, right? Fluorine, chlorine, bromine, they're all diatomic elements at room temperature. And they're nonpolar. So how do they hold together? Well, fluorine is a small molecule. Difluorine is a small molecule. Chlorine is bigger. Bromine is even bigger. So as you increase the size, you get an increase in boiling point because the London dispersion forces are increasing with size. And you find that difluorine has a very low boiling point. Chlorine is not so low. And bromine actually at room temperature is a liquid because it boils at 59 degrees C. All right. So the strongest of these bonds is hydrogen bonding of the intermolecular forces. All right. And this goes back to what I mentioned earlier. Which is stronger, the intra or the intermolecular forces? Intramolecular forces must be stronger. If they're not, you don't have a molecule anymore. All right. Okay. So which of the intermolecular forces are stronger between these two, nitrogen and water? Water. Hydrogen bonding for water versus London dispersion forces for nitrogen. And that the evidence there is in their boiling points. Oh, this is the example I gave you earlier, dimethyl ether versus ethanol. Now, ethanol has the hydrogen bonding ability in one end of the molecule. So that gives it a higher boiling point than dimethyl ether, which is symmetrical and has no dipole moment. Right? It's the only thing that can hold it together is London dispersion forces. So what do we mean by behaving ideally? Ideal behavior. What we're talking about here in ideal behavior is essentially no intermolecular interactions. Right? We just got billiard balls bouncing off each other. So in order to answer that question, you need to know, first of all, is the molecule polar? Right? If it's polar, then it's going to behave less ideally because when they approach one another, there's always the possibility of attraction or repulsion, depending on their orientation. So when we look at dinitrogen, right, we've drawn this molecule before versus carbon monoxide, right? They both have triple bonds. They both have lone pairs out here. But dinitrogen, these are both the same. They have the same electronegativities. They draw electrons with equal force. So this is a balanced, perfectly covalent bond. Whereas this one, oxygen has a stronger attraction. It's going to deliver electron density closer to the oxygen than it is to the carbon. This has a dipole moment. It's not very big, but it's significant. So the one that behaves more ideally is nitrogen. And there's the explanation. Now, in general, for any gas, the more ideal behavior of a gas is seen at high temperature, low pressure, and low moles. These two, the low moles and low pressure, minimize interactions. If you're under high pressure, then you have more chance for interaction of the molecules. High temperature gives them more disruptive potential. And that overcomes any attraction that they're going to experience when they encounter one. So under what conditions do we have high temperature and low pressure? Well, compared to absolute zero, right, 293 K is what we are right now. That's high temperature. Low pressure is 1 atmosphere or less. Actually, we can go up to about 10 atmosphere and still consider it ideal. But if you go to 100 atmospheres, then you're in different territory. All right. Let's see. To hide some helium-filled balloons for a birthday party, you decide to place in a chest freezer. When you retrieve them, you're disappointed to find the balloons deflated. Well, if you've had this class in this particular chapter, you're not disappointed because you know it's going to happen. As they warm up to room temperature, they return to their original size. What gas law is demonstrated in this scenario? Well, what are the two variables? Temperature and volume, right? That's Charles' law. That's the gas law. So it's either C or D. What happens to the kinetic energy of the helium during the warming process? The kinetic energy increases because it's a kinetic energy, average kinetic energy of the molecules is measured by temperature. So we increase the temperature, we increase the kinetic energy, and that makes D the answer. And we've got one more. Okay. Erase this one. Might have to draw a picture for this one. A gas-water displacement experiment, like I described earlier, is set up, and it's determined that 0.812 grams of gas displaces 300 milliliters of water. The atmospheric pressure is 750 millimeters of mercury. The temperature is 20 degrees. Partial pressure of the water is 18. Determine the molar mass of the gas using the ideal gas law. Yada, yada, yada. Okay, so let's draw a picture. There's our water vat. And here's our catcher, our inverted graduated cylinder. Right? So, and we've got a gas being delivered here. Into that. And it's making bubbles and it's filling it up to such and such a point. This is well, I don't know what's happening in that cylinder. Could be a chemical reaction. Let's see. Displaces 350 milliliters of water. So this is going to be 350 milliliters. That's the displacement. 0.812 grams of gas. So we know that we produced 0.812 grams of gas over here into that place. Remember, reading from back to front, molecular weight or molar mass is equal to mass divided by the number of moles represented. So we've got the mass already right here. What we need to do is find out how many moles. So atmospheric pressure is 750 millimeters of mercury. So 750 millimeters of mercury, bearing down on that. And the temperature of water is 20 degrees. See? And the vapor pressure of water at 20 degrees is 18. With vapor pressure of water at that temperature is equal to 18 millimeters of mercury. Okay. So what's the pressure inside here? Well, the pressure inside is the same as outside. Assuming we have this layer, this level down here. Right. Right. If it's up here, then we've got a problem with our difference in height. And let's assume for the moment that pressure inside here is 750 millimeters of mercury. That's total pressure. So that's equal to the pressure of the gas plus the pressure of water. So we know that the pressure of the gas is going to be 750 minus 18, which is 732, right? Millimeters of mercury. Okay. So we're given anything else? Well, the gas constant. Okay. We need to find out the number of moles. So if PV equals nRT, then N equals PV over RT. But if R is liter atmospheres per mole K, we got to change this temperature, which should be the temperature of the gas also. 273 equals 293 K. Okay. So we have pressure times volume over R, 0.08206. And then temperature is 293 K. What's the volume? Well, 350 milliliters. That's the volume for the gas. It's the volume for both of the gases. But it's the volume for the gas we want. But that's milliliters. We need liters. So how many milliliters in a liter? 1,000. Mm-hmm. So we got 0.350 liters. And then we need pressure. 732 millimeters is how many atmospheres? (732) divided by 760. Is 0.732. Equals 0.963 atmospheres. 0.963. So now we can calculate the number of moles. So let's see, that one times 0.35. I better do that again. I think I hit the wrong key. There we go. And 0.08206 divided and 293 divided into that. So I get number of moles equals 1.402 times 10 to the minus 2. So this is going to be 0.812 grams per 1.402 times 10 to the minus 2 moles. And I get 58 grams per mole, which is A. Oops. Oh, I worked it out. Okay. We've got it here in slide form also. This is what we're given. Right. That gives us the pressure of the gas, right? We have to subtract 18 from it first and then convert it to atmospheres. Then we had to calculate the number of moles. That's what that does. And then there. Then we calculate the molar mass. Okay. So these problems, read them from backward, from bottom to top, or from end to beginning. It's the same way you read a posted government regulation that they want to make, right? They have to post it for so many days. Start at the back, don't start at the front. All right, that's it.